So in this problem, we're given two different pieces of information, right? The first piece of information tells us the displacement away from the natural length of this spring when you hang a mass of 10 grams on the spring vertically. The second piece of information tells us that if we replace that mass with a 25-gram block, then the mass will oscillate in simple harmonic motion. And then we're asked to find the period of that oscillation. So the first part of solving this problem is going to involve finding the spring constant K. So here in this diagram, I've indicated that the natural length of the spring is L, right? We don't actually know what L is, but it's just some number, it's the natural length. And then when we stretch the spring some distance away from that length, so I'm calling that distance S, then we know what the force is by Hooke's law, right? So in this case, the distance away from the natural length is 3.9 centimeters. And they tell us that the mass of this object is 10 grams, right? So we know actually what the force acting on this block must be. It must be the weight of the block, right? It must be the force from gravity. So we can just use Newton's second law to determine what the spring constant must be. So the net force on the block is going to be the force from the spring, which points upward, right? It's opposite the direction of the stretching. And just as a matter of convenience or a convention, I'm going to define the positive x direction to be downward. So the contribution from Hooke's law then is minus k, we don't know what k is yet, times the displacement away from the natural length of the spring, right? And that here I've just denoted as s. Then we have another contribution to the net force that's going to be the weight of the block, so it's mass times little g. And this entire thing has to be equal to 0 because this is an equilibrium, right? It's just a mass hanging from a spring. It's not moving in the problem setup. Now all we have to do is rearrange this equation for k. So I'm going to add ks to both sides, and then I'm going to divide by s. And then we get that the spring constant k is mg divided by s. And if I just plug in all of our values, well, m is the mass of this block. That's 10 grams, but we need it in kilograms for the units to work. So that's 10 times 10 to the minus 3 kilograms. G, little g, is 9.8 meters per second squared. Divided by s, the distance that the spring is stretched away from its natural length. Well, that's 3.9 centimeters. So that's 0.039 meters, which turns out to be 2.5 newtons per meter. Right, so for every meter that you stretch this spring, you get an additional 2.5 newtons of force in the opposite direction. Okay, so that's great. That's the first part of the problem that we need. We need this in order to calculate the period of the oscillation later. Now I've just noted here that mg, the weight of this block, which points downward, is equal to ks in magnitude. Ks is the force exerted by the spring on this block, and it points upward, right? So this is this force here, right? And this is known as the equilibrium position of this object. The equilibrium position is different in this case from the natural length of the spring because it's hanging under gravity. So that's going to be important for the next part of this problem, which is going to involve writing down Newton's second law again. So the mass times the acceleration is again equal to minus kx plus mg. Right, so again, this term here, kx, is from Hooke's law. This term mg is just the weight of the block. And remember that we're replacing this 10-gram block with a 25-gram block. So there is something that changes there, but it's only the mass of the block that's changing. The spring remains the same. And in order to determine what the period of the motion is, we need to solve this equation, and then we'll see at the end that something that helps us find the period will pop out. Right, so x here is actually, again, going to be the displacement away from the equilibrium position. So really I shouldn't write kx. I should write k times x plus s plus mg, right? So remember, s was the distance away from the natural length of the spring that we had here. And if I'm stretching it even farther, right, if I stretch the spring even farther away from whatever its natural length is, here's L, and then let's say that this extra distance here is S, but I want to stretch it even farther than that, an additional distance X, like this, then the displacement away from the natural length, which is what we care about for the purposes of Hooke's law, is going to be X plus S. Okay? Oops. Let's get rid of this to make some room. And if we write this out a little bit more fully, if I just multiply this out, minus kx minus ks plus mg, well, from earlier, we remember that minus ks, or ks, positive ks, is actually equal to mg, right? Because this was the equilibrium position for this block. And so these two terms can actually cancel out. And then we end up with minus kx. And there's a subtlety here that I need to point out, which is that S here may not actually be the same as S here. Now this turns out to not actually matter for the purposes of our calculation, but S is the displacement away from the natural length of the spring for this 10 gram block, which will be different for a 25 gram block. So here S is going to be some other number, but it's still true by the definition of what S is, that Ks will be equal in magnitude to mg, right? We just define S to be the distance away from the natural length of the spring that it's going to be sitting at when you hang this mass under gravity, regardless of what the mass happens to be. And so we end up with this second order differential equation for the position of the mass that says the mass times the second derivative of the position with respect to time, that's just the acceleration, is equal to minus k times x, which means that that same second derivative is equal to minus k over m times x. And x, remember, is the distance away from the equilibrium position, which is just the natural length of the spring plus this quantity s. And we can just think about this for a second and essentially just guess the solution to this equation. What kind of function x of t is going to be proportional to its second derivative? It turns out that we have a couple functions that satisfy that. The easiest ones to use right now are going to be the trigonometric functions, the sine and the cosine. So we'll actually have some combination of the two. So we'll have a times cosine, and I'll put a term in here, omega t, plus b times the sine of omega t. And if we go ahead and we actually check to make sure that this is really a solution to this equation, and we don't know right now what omega is, but if we check to make sure that it actually is a solution, right, so I take the first derivative of my proposed solution to this equation, well, remember that it's a times the cosine of omega t plus b times the sine of omega t. Well, the first derivative of this thing is going to be minus omega times a times the sine of omega t plus omega b, and then this term here was a sine, so its derivative is going to be a cosine of omega t. And if I take another derivative, because we need the second derivative, so the second derivative of the position with respect to time, is going to be, well, this turns back into a cosine, and another factor of omega is going to pop out. So minus omega squared a times the cosine of omega t. And then likewise here, this is going to turn back into a sine, and another factor of omega is going to pop out again. So minus omega squared b times the sine of omega t. And I can actually just factor out this negative omega squared from both terms. And then I'm left with a times the cosine of omega t plus b times the sine of omega t. And this right here, this is just our original solution that we proposed. This term here is just x of t that I proposed earlier. It's just this. Which means that the second derivative of x of t is just equal to negative omega squared times x of t itself. But I already know from earlier, this equation here that we wrote down, what the second derivative of x of t is. It's minus k over m times x of t. So this also must be equal to minus k over m x of t. Now, if I match terms on either side of this equation, this means that omega squared must be equal to k over m. K is the spring constant that we found earlier, m is the mass, and so I can find that omega must be equal to the square root of k over m. And this is known as the angular frequency. Angular because it appears in the argument of these trig functions here. Now, we were asked to find the period of the oscillation, and we can do that by using the angular frequency. So we already know how to find the angular frequency based on these quantities that we have. We found k, we know what m is. But what is the period? The period is how long it takes you to get back to where you started, right? So the period is the amount of time. So we'll call this capital T. It's the amount of time it takes for the argument of the trig function to reach 2 pi, because 2 pi is one full period for any trig function. To return to where you started. And so that means that the argument of this trig function, let's say cosine of omega t, after one period, it's going to be in the same place. So we're calling the period capital T. This must be equal to the cosine of 2 pi. And so omega t must be equal to 2 pi. And so now we have a way of finding what the period is, right? This means that the period t is equal to 2 pi divided by the angular frequency, or 2 pi times the square root of the mass divided by k, the spring constant. You can now plug in the values that were given in the problem. So 25 grams, 0.025 kilograms, 2.5 newtons per meter, right? And you can evaluate this using a calculator, however you would like to evaluate it. And the answer turns out to be 0.63 seconds.